Hey Stats, it's Mr. Garby, and here we are in our second to last week of school. We are jumping into a new chapter, Chapter 10, and we're going to really condense this down. We're going to look at two sections today. We're going to really condense it down, and next week we'll be doing the last section of Chapter 10, and that will be it for the year. So, in Chapter 10, what you're going to be doing is taking notes like you have been, and you're going to be doing written work instead of Khan Academy. You're going to have 2 questions for your second assignment. So, let's get right to it for the notes. So, we're going to be looking at confidence intervals. Alright, so, as always, you may print this out, you don't have to, but I've been saying this every week. Statistics is all about making inferences about a sample to estimate the population. And that's really what we're going to be getting into here. So, we use a sample statistic to estimate the unknown value of a population parameter. The confidence interval gives us an estimate, but also a statement of how accurate the estimate is. So, remember, a sample statistic would just be when we look at our sample, a piece of the population, and we come up with some sort of number summary. We're usually looking at X bar. That's a sample statistic for sample mean, or we're looking at P hat, which is a sample proportion. So remember, these are statistics that we're using to estimate the unknown value of the parameter, the population. We can't usually figure out the parameter because the population is too large. So with sample mean is population mean mu, and with sample proportion is population proportion p. So this is a little review right here. Okay, so confidence intervals have the form estimate plus or minus margin of error. The margin of error tells us how accurate the estimate is. So we have plus or minus to say we have our estimate and then the amount above and below. That's why we're adding and subtracting. So a confidence interval can't guarantee to always capture the population parameter. It's not guaranteed that it's going to accurately predict the population parameter. Okay? So there's this thing called the confidence level, and the confidence level tells us how often we capture the parameter in very many uses of the confidence interval method. So basically, this is kind of saying, from a big picture, how accurate is our confidence interval. And that's what a confidence level is telling us. And it's always as a percent. So, the most common confidence level is 95%. If we use 95% confidence intervals very many times, 95% of them will capture the parameter, which means 5% will not. So we would say we're 95% confident that the population parameter falls between this value below as a lower limit and this value above as an upper limit. And we're going to be looking at the formula on how to actually calculate that. So that's the basics of a confidence interval. It's just an estimate plus or minus a margin of error. And it's estimating the population with a given sample. So how do we actually do this? Well, let's start with an example and we'll go through the steps. A survey of 85 randomly selected homeowners finds that they spend a mean of $67 per month on home maintenance. Construct and interpret a 99% confidence interval for the mean amount of money spent per home on home maintenance by all homeowners. Assume that the population standard deviation is $14 per month. Alright, so there's a little bit going on here. We have a survey, 85 randomly selected homeowners. Alright, so this is a random selection. There's 85, so that's our sample size, so n equals 85. From that sample, we have a mean of $67 per month spent on home maintenance. So that's a sample mean, so X bar is our sample mean. It's $67 per month. And then it says construct and interpret a 99% confidence interval. So the confidence level is going to be 99%. So we're going to say C for confidence level is 99%. So this is going to predict based off of the sample of 85 people, which had a mean of $67 per month. This is going to predict the amount of money spent per month for the entire population. And we're also assuming that the population standard deviation is $14 per month. Now, from a practical standpoint, you probably wouldn't ever know this if you don't know mu, but we're starting at a simple level where we're giving sigma, and we're going to move, or we would move, to a different distribution if we didn't have sigma, but I don't think we'll get there in chapter 10. So, it's all kind of the same idea anyways. Step 1 of this, parameter. Identify the population of interest and the parameter you want to draw conclusions about. So what is the population of interest here? The population of interest is, so since the sample is randomly selected homeowners and there's no other information about those homeowners, it's just all homeowners. We don't know where, so we're not going to make any assumptions. The parameter is a mean, right? So the sample mean is a statistic. A parameter is the population mean. And to be more specific, it is the mean amount spent on home maintenance per month by the population, which is all homeowners. Alright, so we just always want to have an idea of what the population is. Conditions. So the inference procedure we're going to be choosing is going to be the same for this whole section, but we need to verify these 3 rules of thumb for using it. Alright, otherwise we can't generalize it. We can't use it to make predictions about the population. So the first is that data comes from a random sample. We always want a random sample, otherwise there might be some third variable involved that we're not considering. The second is that the sampling distribution, as we talked about in chapter 9, is normal or approximately normal. And this is similar to the condition or the rule of thumb we had in last section. So remember, if the population is normal, then we're all set. But if it's not normal, we can use the central limit theorem. So, if population distribution is not normal, the central limit theorem tells us that the sampling distribution will be normal as long as n is greater than or equal to 30. Right? We said a sample size of 30 last time would make the sampling distribution approximately normal. So, if the population distribution is normal, good, we're all set. If it's not normal, the sample size needs to be 30 or greater. The third rule of thumb is individual observations are independent. And what that means is that when I select one thing at random, that doesn't affect the probability of selecting another thing at random. Alright, so the probability doesn't change based off the first or second pick and the outcome of that. Now, if we're sampling without replacement, the probabilities will automatically change because what I'm taking from, the population decreases by 1 each time that I pick, right? Because I'm picking 1, the population decreases by 1. So if we're sampling without replacement, the sample needs to be no more than 10% of population. That's when sampling without replacement. And this, we said this last time, so capital N needs to be greater than or equal to 10 times lowercase n. Remember, capital N is your population size, lowercase n is your sample size. Alright. So, in this case, let's see. Does the data come from a random sample? Well, it said randomly selected homeowner, so that checks out. Is the sampling distribution approximately normal, or is the sample size greater than or equal to 30? Is the population distribution normal? Doesn't say anything about that, so we need to make sure n is greater than or equal to 30, which it is, so we're using the central limit theorem to say the sampling distribution is normal. Are individual observations independent? It doesn't say, but let's see. Is capital N greater than or equal to 10 times lowercase n? Well, lowercase n is 85, right? So let's plug that in here. Is capital N greater than or equal to 850? Now remember what capital N represents. That's population size. And our population here is all homeowners. So are there more than 850 homeowners in general? Any in the United States, in the world? Either way, yes, right? So this checks out as well. Okay, so that was step 2, check our conditions. Step 3 is do the actual calculations as long as the conditions are met. We're going to use the general formula for confidence interval. The general formula, like we said before, is just the estimate plus or minus the margin of error. So the estimate we're using to predict the population mean is simply the sample mean. So our estimate is going to be our sample mean, which is x bar. The margin of error is going to be the critical value z. We're not going to get deeply into what that means, but I will tell you how to use it, times sigma, which is the population standard deviation, divided by square root of the sample size, which is lowercase n. So, basically our formula for confidence intervals of a mean is x bar, which is our estimate, plus and minus the critical value z times sigma divided by square root of n. So, let's first talk about this critical value. This is based off of just like a z-score and a normal distribution. So all I'm going to give you is this simple little chart and what the value of z is going to be based off of the confidence level. Oh, that should be confidence level. So if we have an 80% confidence level, like it says construct an 80% confidence interval, that's an 80% confidence level. Z is going to be 1.28. Another common one is 90%, which would be a critical value of 1.643. Another common is 95% confidence interval, which would be a Z of 1.96. And the 99% confidence level would be 2.576. This is all from that table A in the front of your book, based off of a normal distribution. These are really just z-scores. Alright, so What we're going to do now is just plug in what we need, and we're going to get our answer. So, like we said, x bar 67. So that's plugged in here. Plus or minus critical value z. Alright, so this one's a 99% confidence interval. So we're going to use 2.576 times sigma divided by square root of n. Sigma is 14, n is 85. So we have times 14 over square root of 85. And yeah, so graphing calculator. Always try to prevent rounding until the end. So what I'm going to do first is find my margin of error. So I'm going to take 2.576 times 14. Take my answer, just press the division symbol. And then I'm going to divide it by square root of 85. So I'm going to go square root, oops, delete that. Square root of 85. That's my margin of error. So I'm going to have 67 plus or minus 3. Let's go out 4 decimal places. 9,117. Yeah, 3 is fine. All right, 911. Wait, what did I just do? 3.9117. Yeah, this is really just up to you how you want to round it. I would go with at least 2 decimal places, but I went 4 for fun. So now we have to add to our estimate. So 67 plus 3.9117. Now, for the sake of writing it, I rounded. If you want to be super exact, like we've been doing, you can do 67 plus previous answer. The only pain about that is when you go to subtract it and you want to take previous answer, it's not going to be this anymore because I'm going to have a bunch of calculations. So I'm not going to be as picky about that. I'm just going to go with this. So we have, when we added 70.9117, and then let's do the subtraction. 67 minus 3.9117. 63.0883. Now the way we write this answer is we have the lower number as the first number in the parentheses, and the higher number, which is like an upper limit, is the second number after a comma. So this is how we would write our answer. Now, this means nothing if you don't know how to interpret it. So let's step 4, interpret your results. So the way we would interpret any confidence interval like this, I'm just going to give you like a general way to interpret it. You would always say, we are C%, so C is confidence level. In this case, it's 99. Confident that the true mean, so when I say true mean, I mean population mean, right? The mean of the entire population is between this first number, which we got by doing the subtraction, so that's x bar minus critical value z and standard deviation of square root of n. So it's between this and when we add it. So x bar plus critical value times standard deviation over square root of n. Okay. So we always want to be specific. That's just a general way to write it, and you can kind of plug stuff in there. So we would just say where 99%, because our confidence level was 99%. That's what they asked in the question. We're 99% confident that, so instead of saying true mean, since I have some context here, I'm going to say the population mean, or the mean amount spent for all homeowners per month for home maintenance is between Alright, let me just put it in words. That the mean amount spent for monthly home maintenance for all homeowners is between these two numbers. So this is dollars. So let's go to the nearest penny. 63.09 and 70.91. So base of our sample, standard deviation, sample size, confidence interval we were given. We're 99% confident that the average homeowner out of all homeowners spend between this amount and this amount per month. So it's a prediction or an estimate about the entire population, right? That's what we did there. All right, so I'll do one more example, and you'll have to do 2 of these for your formative, in addition to the notes. You want to rent an unfurnished 1-bedroom apartment for next semester. The mean monthly rent for a random sample of 10 apartments advertised in a local newspaper is $540. Assume that the standard deviation is $80. Find a 95% confidence interval for the mean monthly rent for unfurnished 1-bedroom apartments available for rent in this community. Let's get rid of that. So the parameter. So what we want is, in this entire community, the mean monthly rent for an unfurnished 1-bedroom apartment. And we have a sample of 10. So the parameter would be the population mean. So it would be mean cost of renting an unfurnished 1-bedroom apartment in this community. So the population would be the mean. If we had all the costs, right, and we took the mean, of course we're going to estimate because we only have 10. We only have a sample. So is this a random sample? Going back to our conditions. Well, it says it's a random sample. So we're going to say yes. Does it say anything about being normal? No. Does is n greater than or equal to 30? If so, we can use the central limit there. No. N equals 10. Well, okay, so that condition isn't met. So, since we can't really have the sampling distribution be normal, we don't have the proper inference procedure for this, so we're going to stop. Okay? So we can't assume sampling distribution is normal. Right? We've only been dealing really with the normal distribution, so we're going to stop because the conditions aren't met. So that's it. You would stop. So you watch out for that in your homework. That might happen. But if it doesn't, it's really all the same formula. You have X bar, you have your Z based off of your confidence level. This will be given, this will be given. Calculate it out. Use this as a template and just kind of replace the numbers. And I think it would really just be that easy. So that is it for these notes. That's very much in a nutshell chapter 10.1 and 10.2. So you can print that, you can write it out, but that's the first part of your formative. The second part is going to be 2 questions. Make sure you show your work and follow this 4-step procedure that I have showed you how to do. I will have one more video for next week, and hopefully I'll see most of you at graduation. Looking forward to it. See you guys.